ladies and gentlemen. Today we are talking about medians and altitudes, section 5.4. And this is one of the more challenging sections in the unit, so I think this might be a more viewed video. But just to make a note, we're still talking about segments within triangles. This whole unit is on relationships within triangles. We talked about mid-segments and angle bisectors and perpendicular bisectors. So this is continuing that same flow. We know that median in probability and statistics is talking about the middle number in a series of numbers. When you order them from least to greatest, this one appears in the middle, or the two middle numbers. You can take the average of the two middle numbers if you have two medians. But if we're talking about triangles, we're also talking about something in the middle. The median is a segment that's drawn from the vertex to the midpoint of the opposite side. That is what's considered a median, from the vertex in a triangle to the midpoint of the opposite side. So if I have this triangle down here, if I were drawing this segment from my vertex A to my midpoint on the other side, this is considered to be median. If I draw a segment from B to the midpoint on the opposite side, another median. Same thing from C to the midpoint on the opposite side. That's another median. And as you notice, these three meet at a single point, and that single point has a fun name. A lot of people find it interesting. No, I don't make these up. This is called a centroid. The centroid is your point of concurrency, where those three medians in a triangle intersect. Now, with the centroid, there are some special properties involved. Theorem 5.8 talks about the medians and they intersect at the centroid. The medians of a triangle, as it says, intersect at a point that is 2/3 of the distance from each vertex to the midpoint of the opposite side. So let's say we're taking this first median here. That means that this centroid is 2/3 the distance from A to E. So this is 2/3 of the way over. So this is 1/3 right here. And let me make it a little smaller. And this is 2/3 right here. This is 2/3 the distance. This is the other third. So that's the centroid. It kind of divides your medians into 2/3 and 1/3. And if you like to look at an expression, here we're dealing with I'm going to call this P as part of it, and then AE is the whole thing. So AP, the part, equals 2/3 of the whole thing, AE, if I'm looking at this segment here. So A to P is 2/3 of A to E. That's what the centroid does. It divides it into a 2/3 portion and a 1/3 portion. Now it's going to make much more sense when we use that to solve problems. So let's solve a couple of problems to solidify what we know about that. So here we're given a triangle RST, and we know that Q is the centroid and that SQ is 8. Find QW and SW. Well, we know that the centroid is 2/3 the distance across this median. So 8 is 2/3, and then we have another third down here, and we're looking for the whole thing. So our whole thing here is SW. This little part we know is SQ. Well, SQ is 2/3 of the whole thing. So from S to the centroid is 2/3 the distance of S to W. It's 2/3 of the whole thing. We can use this setup to solve for our missing piece because we know SQ is 8, so we'll use our substitution property. And if we want to solve for SW, to get rid of this 2/3 we're multiplying by, you can divide both sides by 2/3, or more appropriately, multiply by the reciprocal. So times 3/2. So these cancel, and 8 times 3/2 will give us a value of 12. So this whole thing is going to be 12. We know that 8 is 2/3 of the whole thing. 8 is 2/3 of 12. And to find this missing piece, if the whole thing is 12 and this piece is 8, the other remaining piece must be 4, because 12 minus 8 equals 4. So we know that our other piece, QW, is going to be 4. Simple segment addition postulate. We did that way back in chapter 1. So there's an example. Again, we know this is 2/3 of the whole thing, so 8 is 2/3 of SW, so we know SW must be 12. Let's do another example involving this, maybe a little bit more challenging because we're going to deal with some graphing. So the vertices of triangle FGH are, and they're given, which ordered pair gives the coordinates of the centroid P of this triangle? So let's graph this first to give us a visual. So I'm going to graph my points. I have f at 2, 5, so right 2 and up 5. I know that g is at 4, 9, so right 4, and this is 7. Let me draw a couple more lines, 8, 9. And h is at 6, 1, so over 6, 3, 6, up 1. And then here's my triangle. Well, the first thing we need to do if we're looking for the centroid is we need to draw in a median, because we know the centroid is on a median. It's on all three medians. But we only need to use one for this type of problem. Well, to find a median, the first thing you have to do is find a midpoint, because a median goes from a vertex to a midpoint. So I'm going to pick FH, and I'll show you why in just a minute. And I need to find the midpoint of FH. I can do this one of two ways. One, I can find the coordinates of F and H, and I can use my midpoint formula to find the coordinates of my midpoint. Or I can use slope in this particular case. My slope here is -1, moving down 1, right 1, down 1, right 1, all the way over. Well, I move down 1, right 1 4 times. Half of that is 2 times. So 1, 2, there's my midpoint. It's a nice little shortcut we can use with slope to find it in a problem we're trying to save some time on. So in this case, the coordinates of my midpoint are over 4 and up 3. So we found our midpoint. Second thing we need to do is draw our median, which will go from the vertex down to this midpoint on the opposite side. And that's why I chose that as my midpoint, because here I have a vertical line. No distance formula will be required here. What we will have to do is find the length of our midpoint. I'm going to call this M here. This point here is M. So I'm going to find the length of GM, because I know the distance from G to my centroid will be 2/3, whatever the distance from G to M is. Well, from G, which is up here at 4, 9, down to M, which is 4, 3, that's 6 units. I can just count them. No distance formula required. And if I want to find the location of my centroid, it's 2/3 times that distance. So in this case, my centroid is 4 units away from G. So I'll say units from that vertex. So I'll start here and I'll move down 4 units. 1, 2, 3, 4. That, ladies and gentlemen, is our centroid. Usually you see the point of concurrency labeled as P. And my location here is on right 4 and up 5. In that case, my answer is B. Again, we're using the same property that your centroid is 2/3 the distance between that vertex and that midpoint. We have to use that quite often. So there's a couple problems dealing with the centroid and medians. The second piece of our lesson today deals with altitudes. Most people think of altitude in conjunction with airplanes. Altitude is talking about the height of an airplane. Well, remember, we always measure height or any sort of distance perpendicularly. It's never at a slant. So in this case, an altitude is talking about the height, but it's really talking about a perpendicular segment. And it's the perpendicular segment from vertex to the opposite side. That's an altitude. And usually when you're finding the area of a triangle, and you have to use the height, your height is an altitude. So it's still in conjunction with height like it's in an airplane. In an acute triangle, your altitude is inside. Obtuse triangle, it's outside. And then in a right triangle, it's on, which you've seen many times. Your altitude is just one of the sides that forms that right angle there. So in this case, these are examples of altitudes. And usually you'll see them as dashed lines when they're outside, just to indicate they're not a part of the actual triangle. If you're finding like the area of this region, you don't include this out here. This is just to illustrate what your height is, what our altitude is. Altitudes of a triangle intersect at one point as well. So these 3 altitudes of a triangle are concurrent. And here they meet at point G, which in this case is outside the triangle. We don't have to know any sort of special properties about it like we did with the centroid, just the name, and this is called the orthocenter. Now I know that all these different lines, all these different points of concurrency can get confusing, so make sure you utilize the chart that I have in the classroom for reference, so you can easily organize them, organize your thoughts. So just know for now this is called the orthocenter. Well, in general, the orthocenter can be at different places in your triangle as well. And we'll examine this in a moment using some software, but for now, just know that in an acute triangle, it's going to be inside. Right triangle, you're probably guessing this now using inductive reasoning pattern recognition. It's on the triangle. And obtuse, like I mentioned, outside. That's where your orthocenter is located. Just so that you know, at various times, you might see your orthocenter at these various locations in the triangle. That's a bad-looking triangle, but you know it's a triangle. So, you might see that at different locations. You won't necessarily have to use that to solve any sort of specific problems, but it's good information to know so that you are not surprised that something is outside the triangle when you thought, hey, I thought it was only inside the triangle. But this is when the lesson gets interesting. Talking about isosceles and equilateral triangles. Let's look at some of this. So here, I have a triangle I've drawn, and I have 4 different line segments. I have in blue my median from the vertex down to the midpoint. Notice I have another line through the midpoint. That's our perpendicular bisector. Bisects it, so it also goes through the midpoint. My black line is my altitude. Notice here it's a right angle, so I know this is my altitude because it's perpendicular. It's also parallel with my perpendicular bisector. They're both perpendicular here. And then my angle bisector is in green. This is just your plain old scalene, nothing special triangle. But watch what happens if I make this an isosceles triangle. If I make this so that both of these segments are the same, what do you know? All 4 of my special segments are exactly the same. They're all overlapping. My median is the same segment as my altitude, which is the same as my perpendicular bisector and angle bisector. So, in an isosceles triangle, all 3 of these segments are actually the same. They're different properties, but they all happen to be the exact same. You're dealing with an isosceles triangle. So, in an isosceles triangle, we know that they are always actually the same segment. They all do the same thing. The median is the altitude, which is the angle bisector, which is the perpendicular bisector. Now, since an isosceles triangle we have is a 2 or more sides are congruent, an equilateral triangle is really just a special type of isosceles triangle. So in an equilateral triangle, it also holds true. Now this is where it also gets just a tad bit more interesting. Notice these points. I have my centroid in blue, and remember that's where our medians intersect. I have my orthocenter in black. That's where my altitudes are intersecting. I have my circumcenter in red, which is where my perpendicular bisectors are intersecting. In center, where my angle bisectors are. Now, with the orthocenter, notice if I make this an obtuse triangle, it's outside. The black dot has moved outside my triangle. If I make it a right triangle, it's on it. In acute, move that, let me actually undo this. In an acute triangle, it's going to be inside. Now notice, this is now an isosceles triangle. Let me move this out of the way. And all of these points appear to be, what do you know? Collinear. Because all of the segments, the altitude, the median, etc., they're all overlapping. So all these points are going to be collinear. So in an isosceles triangle, all your special points are collinear. Very interesting. Let's see what happens if it's an equilateral triangle. If I were to change this when it's equilateral, and I'm just going to pause this because sometimes it can take a moment, so bear with me here. If I make this an equilateral triangle, all of my special points have overlapped onto themselves. So just to give you the visual of how that works, if I move this out, they're all different. If I make this more equilateral, they seem to drift towards each other and eventually will be on top of each other just like that. So, in an equilateral triangle, all of my special points are all actually the same point, which is very interesting. So the centroid, the orthocenter, circumcenter, and incenter are actually the same point in any equilateral triangle. Ladies and gentlemen, that is a brief summary of what we're talking about in this section. I hope this video is somewhat helpful. Feel free to rewind it and check it out. Your textbook is a great resource, and so is khanacademy.org. If you're having any questions, feel free to email me at any time or come see me. This is a challenging section, but I have complete faith in you.